we're going to introduce degree now. So suppose that I'm going to use f for a polynomial. This is a polynomial over some subfield k of c. And f is not 0. Then the degree of f, so this is what we're defining, which is denoted, I'm not too happy with this symbol, but it's what your book uses, so I'm going to stick with it. It's denoted with the partial symbol, so partial f is the highest power of f with non-zero coefficient. So we know that since f is a polynomial over k, I can represent it as a sum where the coefficients are eventually 0. The tipping point where the coefficient goes from non-zero and it stays 0, that is the degree. So, for example, if we wrote r to be, I don't know, 2 plus 3t squared plus 6t to the 4th plus 0t to the 5th, then the degree of r is 4, because the last power with a non-zero coefficient is 4, right? And that's it, okay? The degree is a very powerful thing. It's a very powerful, actually, not thing, but function. So we regard the degree as a function. From the polynomial ring to the natural numbers. Actually, that's not right. This is false. It's not right because I said in the definition of degree we have to have a non-zero polynomial. If we had the zero polynomial, there is no highest power, and we will take it as a convention that the degree of the zero polynomial is negative infinity, and therefore the natural numbers including 0 don't make sense. We need to add on negative infinity, and we're going to adopt the usual arithmetic with negative infinity, namely that negative infinity is less than a for all integers a, that when you add negative infinity to an integer, you get negative infinity for all integers a. When you multiply a integer with negative infinity, you're going to get negative infinity. This isn't quite helpful if a is negative. Technically, you should get positive infinity. However, let me even just clarify it where we're going to need our arithmetic. This is going to be an n0. That makes me feel better. There we go. For all a and n0. And we also declare that negative infinity squared is negative infinity. And the reason is for the next proposition, where we're going to really investigate this function, and then you're going to investigate this function more in your homework. So proposition, oops, wrong color. If fg are polynomials over k, then the degree of f plus g is less than or equal to the max of the degree of f and the degree of g. So that's A. And B, the degree of the product is the sum of the degrees. So let's just take a minute and prove this real quick. I guess before we prove it, let me just point out something. This guy here says the degree is not additive. This guy says the degree is multiplicative, or sometimes people say additive here. I prefer to use the word multiplicative. But it's kind of like the log. It takes multiplication to addition. Okay. So the degree takes multiplication to addition. It does not break up under addition though, and it does not break up under multiplication. And this is something that we kind of know already from doing years and years of polynomial arithmetic, but it's worth saying that. So let's start with A. So write F is sum on Ri t to the I and G as sum on Si t to the I. Suppose n, well, suppose the degree of F is M and the degree of G is N. So all that means is that Rk is 0 for k bigger than M, and Rm is not 0. It also means that Sk is 0 for k bigger than n, strictly bigger than n, and Sn is not 0. Okay, so Sn is the leading term of G, Rm is the leading term of F. Then, if n equals max of M and N, the sum F plus G, which is sum on Ri plus Si t to the I, satisfies the degree, or sorry, satisfies rather Rk plus Sk is equal to 0 for k strictly bigger than n, because it exceeds both the lower bound. Let me fix that bigger than sign. It exceeds both n and m, because big N is the maximum of them, so it's bigger than both of them. However, we do not know, so it could be that m equals n and Rm equals negative Sm, in which case the degree actually goes down. For example, if G was negative F, then F plus G is just 0, right? And so the degree of F plus G is the degree of 0 is negative infinity. So it could be that that's true. We don't know. And either way, the degree of F plus G can be no more than n, which is, of course, the max of the degree of F and G. It cannot exceed capital N. And it could be less than, and you'll investigate that on your homework, trying to find polynomials where it is, in fact, less than. And I actually already gave you an example of one. So that's the proof of A. For B, let's keep F and G as before, then the product, F times G, is this big sum, right, of this Qj t to the j, where Qj is the collection of all pairwise products of RHSI. And let me just notice something here. Let me claim something, that Qj is 0 for j bigger than m plus n, which means that F times G has 0 as its coefficient above the proposed degree, right? For B, we're trying to show the degree takes, the degree of the product is the sum of the degrees. And so why is that? Well, in this case, if H is well, let me say it this way. If H is bigger than M, so that's the situation where RH is 0. But also, H being bigger than M says what? Well, H plus I is J. So J equals I plus H is bigger than I plus M. But, sorry, I could have presented this slightly. Let me write this slightly differently. So we know we're assuming that j exceeds m plus n, but we know that h plus I is j, so that's an h plus I. Oh wait, sorry, I think I see where I've confused myself. All right, sorry, sometimes this happens. Let me just back up a second. I think what I want to say is if h is less than m, so no, I do want to say if h is bigger than m. Oops. If h is bigger than m, then RH is 0. So RH times SI is 0. So this means that for all the indices where h exceeds m, the contribution in the sum is 0. And if h is less than or equal to m, then we have that, well, on the one hand, h plus I is j. On the other hand, we know that we're in this situation where j is bigger than m plus n. And on the other hand, we know that h is less than or equal to m. So I can replace the m there with an h. And then if we subtract h from the left side and the right-hand side, we're going to get I, and then we're going to read this as that's a weak inequality there, so that stays. And on the far right-hand side, we have n. So if h is less than or equal to m, then I is bigger than n, and so SI is 0. Thus, the contribution here is still 0. So whether or not h is bigger than m or less than or equal to m, the term in the sum is 0. Okay, so all this is saying is f times g doesn't have terms above the proposed right answer. All right, now let's show that if j equals m plus n, then qj is equal to what we think it is. The product of the leading coefficients should be the leading coefficient of the product. All right, so what do we know? We know that qj is this big sum, and we know, RHSI. Sorry, this video is going a little bit longer than I thought it was going to be. That's okay. We know this, that's just the formula, and we know that we're going to get Rm Sn as one of the indices where h is m and I is n, because they certainly add up to j. That's the situation that we're in for this second and last part of the proof. And then we're going to get sort of everything else. What are the terms that show up in the all else part? Well, they're terms where the index for h is either less than m or the index for h is bigger than m. Okay. In the case where h is bigger than m, our HSI is 0 times SI, because the degree of our polynomial f, the guy that controls where the coefficients of r come from, has degree m, so we're past the degree. If h is less than m, then what? Well, h plus I is j. J is also m plus n in this proof, and h is less than m. So we can replace the h with a bigger expression, m plus I. And now if we subtract m from both sides, we're going to get I is bigger than n, like we saw on the previous guy. So in this case, RH times SI is RH times 0, because we're above the degree for the S coefficients, and we still get 0. So my point here is the all else becomes 0, because it's a sum of zeros. And so Qj is Rm times Sn, and then lastly, Qm plus n is Rm times Sn, and then lastly, this expression is non-zero, as Rm and Sn are not 0, and we are, of course, in a field, so there's no zero divisors. Okay, so that was sort of longer than I expected. Sorry about that. But the degree of a sum is less than or equal to the maximum of the degrees, and the degree of a product is the sum of the degrees.